Hey, this is part two of some videos I was making on making some analog RF modulators or radio frequency modulators. The first part I looked at making a simple AM modulator, and this one I'm going to have a look at making an FM modulator. I'm going to have to do some surface mount device soldering to get this one to work. I haven't done that before, so first part of this video probably looking at doing some SMD soldering and see if I had any luck with that. And then later on in this video I'll put the FM modulator together and test it out. And then I actually found out that there's a thing called a TinySA that I got that you can use as a spectrum analyzer, and it has a fairly nice signal generator that does FM and AM modulating anyway, so if I knew about that I probably would have made these two things, but live and learn, I guess. I got the design for my FM modulator off this Afro Tech Mods website. It was actually on YouTube. It's this one here, so let's dive into that project that they did. And like I said, there's a nice YouTube video on that. And the thing you want to look at is pull down these design files. Let's have a look at that. And it's got information on it like the schematic. It's basically two parts to this design. There's a precision voltage regulator here. It runs everything internally on 3.3 volts, which is good for the stability of it. And then the actual design, which uses this MAX 2602 chip, which is a voltage controlled oscillator for getting the FM working. There's a nice breakdown of how to place the components. Again, these are SMD components on the board. And a bill of materials, so the guy did a pretty good job of breaking down where to buy the components you need for this and the actual sizes for the components here. You can get it from places like DigiKey, Mouser for this. So let's have a go at firstly I'll get a copy of the boards and then the components I need, and then try doing some SMD work to put it all together, which could be a disaster. The actual PCB board that I used to mount the SMB components I got from Ausch Park, and you can see here's the order screen. You can actually get there from the Afro Tech Mods website for this board, and you can see here it only costs $2.85 to get them printed and sent to me, so pretty good deal. They do them in batches, so it could be up to a month for these to arrive, but they seem to do a nice job. So I'll go through how I soldered the little SMD components to the PCB board. So I use solder paste. So see here, I just got some solder paste, and I'm using a microscope to get a closer view of the PCB as well. And first thing I want to do is just put a bit of the paste on the contacts on the board. So I used like a little pick to do that. It doesn't have to be totally accurate, because when the solder paste melts it flows onto the contacts, the copper contacts anyway. So if you're doing this in big time manufacturing, you'd be using a silk screen to get it exactly over the contact points. I use this little hand vise you see here too. That turned out to be fairly useful for keeping everything in one place. Otherwise I'd probably have to tape things down, which would be annoying when I had to move them around. So first time I did this, I just put paste on where the resistors and capacitors go. And I started using tweezers to position everything on the board. And Initially I tried doing this through the microscope, but that's a little hard to be sensitive to how to move things, so I found it was better to use binocular magnifying glass to do this stuff. After that I use a heat gun to heat the solder paste. Looks kind of ugly here, but as it starts to flow and heat up, the solder actually gets attracted to the copper contacts and starts to look a lot better. But you see, one problem here I had with doing this was the C5 capacitor didn't seem to be exactly the right size for the spacing of the contacts, so it kept roaming around on the board. So I think it's important to make sure you've got components that are the right size. It's really hard to get it right. So this is the result after the first attempt at soldering the board together. It looks kind of ugly. There's kind of flux hanging around on the board, but I did put some pins in to pull some of the key contacts off. I found once I put this together and tested it, this board didn't work. I think I might have either melted the variable resistor or the IC. So this is a second attempt at doing the same thing. I used more flux, which is kind of why it looks a little uglier, and I also used a soldering iron because some of the contacts were bridged together on the IC. Some things I learnt while doing the SMD soldering. So first I used the method of using solder paste and hot air rework station. I found best temperature in the end was to set the temperature on the station to 300 degrees Celsius and use a very low air speed, otherwise I was blowing the components off the PCB. You have to make sure that you're using the correct size SMD components. I had trouble positioning one capacitor that seems to be a little long for the PCB. If I had trouble with the soldering, I used a little dab of flux and just a normal soldering iron to clean up some of the connections if the paste didn't flow nicely. An example of that was for the IC. I had a couple of legs that were bridged by the solder paste even after I used the heat gun. I didn't want to heat up the IC too much, so I ended up putting a little bit of flux on that and used a normal soldering iron just to get the solder to reflow onto the pads and away from the legs. For doing this I had the most success when I used a binocular magnifier when soldering. It was easier to get the depth perception right for when I was using both the rework gun and soldering iron. And then after that I used a multimeter with the continuity tester to test that I didn't have any solder bridges or connections between pads that were close by, and that the components were actually conducting via the PCB traces to where they should be. And my last big hint was I don't think I'll do SMD soldering again. I found it fairly stressful and didn't really work out that well, so unless I really have to do SMD soldering, I think I'll stick to normal size components. Let's try testing this out. So this is my little SMD PCB. Looks tiny here. I actually took the potentiometer off the board and have it as a separate potentiometer because that's the way I'm going to use it in the case, so I can vary the frequency easily. I've got an FM radio here. This is the power in from my power supply. This is the modulator in coming from my signal generator. So let's turn on the FM radio. So again,
and we
something there.
Appreciate that
so let's
very
turn on
much.
the power supply, which seems to suppress the over the air, which is good. It means it's probably making FM at that frequency. Let's turn on the signal generator. That's pretty loud, so I'm going to actually change the amplitude down here. 100's better. Let's turn that down a bit. But let's actually try taking it down until we... Okay, that sounds pretty good as a pure sine wave. And that comes in at 20 millivolts, so looks like 20 millivolts is the sensitivity to get good modulation on this FM modulator. That's a bit high for what I want to use when I use it in a case, so I'm going to put a resistance divider in here to be able to have a input modulator of up to about 1 volt and have that swing the FM modulator. But otherwise seems to be working. Let's try changing the frequency up here. Okay, that's a good sign. So I think we're good to go. Now, next thing to do is put it in a case. There wasn't an easy way to mount the PCB, so I actually made one here in Fusion 3D and printed it out on the 3D printer so that the little PCB sort of clips into this holder here, and then I can glue this to my case. I'll put a link to the Fusion 360 file for this in the description below. Okay, I decided just to put it in some cases I had hanging around. So it's just a small plastic case, and when I do a test fit it looks like I can put this... I'm actually using a 10-turn potentiometer with a flash dial, vernier dial, to select the frequency. I'm hoping with the stabilization of the built-in regulator that it should hold the frequencies once I put them in. I'll put a little 9-volt battery down here, and here you can see the PCB in its little holder. I'll glue the holder down to the base of the case, and then I'll put a couple of BNC connectors, one for the modulation input and one for the FM output on there. And once I've done all that, I'll see where I can fit a little switch so I can switch it on. I'll put a lead LED in there as well, just so I know when it's turned on. Let's have a closer look at how I mounted the 10-turn potentiometer and the dial that comes with it. So there's some little locators on the washer that need to be aligned. So the hole in the washer aligns with where the nub on the underside of the washer needs to go into. So first I found a location and used the hole as a guide for drilling a little hole into the case. So that's where the nub's going to go. So I drilled that hole. I took the potentiometer out, which is really just a guide to holding the washer on at the moment. Then put the washer back in the other way up, so now the nub in the washer goes into the hole in the case, so it holds the washer in one place, it won't revolve. And there's another little locator on the vernier dial that aligns with the hole in the washer, and the washer's not going to move. So align that so that the dial doesn't turn around by itself. And there's a little set screw to tighten up there to hold the dial against the washer. And you can see here now when I turn the dial, a little indicator tells me how many rotations I've done. So this is the case put together before I wired it up, but I was just making sure that all the major components could still fit in the case. That looked okay. This is where it's been wired up, and the case just has a snap-on back to close the case up. And the two BNC connectors, so I put a label on the front of the case to remember what's what. So the modulation input, which can be 1 volt peak to peak, comes in from the bottom. The FM output comes out from the top. The switch is up the top. You see the little LED turn on, and you can see here I can use the dial to set the FM frequency. And the label there I calibrated to get the dial settings to match the frequencies that I wanted. Let's have a look at some use cases for the FM monitor. So I've got the signal generator and the oscilloscope down here on the bench so I can see them better. So first let's turn on the oscilloscope, connect the input to channel 1 on the oscilloscope to the output from the FM modulator. So no signal at the moment because I haven't turned it on, but I've got it set to the 100 megahertz setting on the dial. So let's turn it on, and we can actually see on the oscilloscope that it's actually registering it as a 100, or pretty close to 100 megahertz signal, even though the oscilloscope only goes up to 50 megahertz. It seems to be able to still cope with up to 100. So next test, I'm going to try the other end of the range, so let's take it down to 87.5 megahertz. So it should be a setting of index 100 on the dial. And we see on the oscilloscope it comes in pretty close to that as well. So the calibration's going okay. Let's try zooming up the range, see if we can pick the top end of the FM scale up okay. And this is where I started having trouble with the oscilloscope. It just didn't seem to go very well at measuring anything up about 102 megahertz, which is not that bad for a 50 megahertz oscilloscope. So I changed over to using this TinySA spectrum analyzer for getting the frequencies calibrated. So again, just took the FM out from the FM modulator, and this time I just connected to the aerial going into the input on the Tiny spectrum analyzer, and you can see it's picking up the frequencies. And this time when I take it up to a dial setting of 72, works okay. And then I take it up to the dial setting to get 108 megahertz, which is the top end of the FM range, so it's registering that okay. So for calibration, I found this TinySA device worked better than using the oscilloscope. Maybe if I had a faster oscilloscope that would have been better in the end. So now let's just test it out with the radio. So I'm taking it back down to 100 megahertz. And I'm connecting up the modulation input this time so I can hear it on the radio. So put a 1000 hertz signal in here as the audio signal into the modulator. And looks like we're picking it up on the radio. So this is the interesting thing for FM radio work, is I can see how close the dial is to the frequency. So I see for 100 megahertz, this dial's about 2 megahertz out, which is pretty bad. Now let's try some of the other ends of the FM spectrum. And now I've set it to the lower end of the FM spectrum. And let's see where on the dial that shows up on the radio. So that one's pretty close, except my dial's a bit weird on this radio. It's got two values for the lower end of the FM spectrum. So there's quite a lot of leeway there. And let's go up to the other end, 108.5 megahertz, and see where it shows up on the dial. Okay, so the lower end and the top end of the dial aren't too bad, but in the middle things are a little out. So this radio I wouldn't expect much from, but for one I was actually doing up, this will be useful for tuning the dials to get them an exact match to the actual frequencies. Here's a little bit more sophisticated use of the FM modulator. So I'm using the oscilloscope, the radio, and the signal generator and the FM modulator to work out what's the frequency response of the radio. So when it receives audio at different frequencies, does it amplify at some frequencies more than others? So the way I set this up is on the signal generator, I've got a splitter on the BNC out of that. So one leg of the BNC's running into the modulation input of the FM modulator, then out of the FM modulator the RF signals going to the radio, and then on the other split of the BNC connector it's going into the second input on the oscilloscope. Now I'm plugging in the audio output from the radio into the first input on the oscilloscope, so I can sort of compare the waveforms, what's been coming out of the signal generator to what's coming out of the radio, so going through the whole FM modulation process. So at 1000 Hertz this is the results, and I've got the peak to peak readings of the output from the radio in yellow. So I'm going to drop it down to 200 Hertz, so I'm just going to get some samples at different frequencies to see what's the output from the radio, and that'll tell me if there's any impact on the output of the radio based on the frequency. So this is 200 Hertz. Now the radio I'm seeing about 640 millivolts. I'm just going to range through different frequencies. I'm just going to go up to 2000, 4000, 8000 and then 15,000 Hertz. So let's have a look at 2000 Hertz. Take a photo of that, and we see we're at 0.92 millivolts, so not much change from the 1000 Hertz results. So let's have a look at 4000. 4000, the output from the radio has gone down to 0.72 millivolts, or 720 millivolts. And we can see on the oscilloscope that trace coming out of the radio is dropping down quite a bit as the frequency goes up. So at 8000 Hertz we're getting 440 millivolts out of the radio. So it does look like the frequency response gets impacted by the frequency of the audio, so higher frequencies of audio seems to be lower output than the lower frequencies. And finally at top of really the normal FM band range at 15,000 Hertz, we're only getting 160 millivolts out. So I graphed the whole thing up, and I went and used a log function on the millivolts output. And the nice thing is we see a fairly straight line, at least above 1000 hertz, which tells me there's kind of a linear impact on the output based on frequency. So it's a good way of diagnosing, you know, how good that radio at giving you the actual audio that was fed into the FM station. Let's have a last look at the TinySA spectrum analyzer. This has a function generator in it, and that does everything I would have wanted from the AM and FM modulators. So when I first turn it on, I'm in the spectrum analyzer mode. I can flip it over to function generator mode. So first I set the main frequency, not like that. I set it to 100 megahertz. And then I select the type of modulation. It can be AM or FM. I'm going to go with FM and set the modulation tone to 1000 hertz. I've got the radio turned on, so let's try running this. And I can hear the tone. And I can change the modulation tone if I want, so let's change it down to 900 hertz. And you can hear a lower tone here. So that works pretty well. And like I said, if I knew it was on the TinySA, I would have used that rather than all these analog versions.